Hey, good afternoon, everybody. Looking at the crowd from this direction, it seems like it's thinned a little bit, but we're here to talk a little bit about noisy judgments, umpiring variability, and so forth. So we're kind of new here, never been to SABR before, so we thought we'd start with a couple of introduction slides. I don't really have a baseball background. My background's in astronomy and astrophysics. I've been playing data scientist for a dozen years or so. Currently work for a consulting company out in DC, lead a team of 15 data scientists doing work for the Air Force's Chief Data and AI Office, and cannot hit a curveball.
Hi, everyone. I'm Emily. I'm Pat. In my day job, I lead a team of data scientists and methodologists for Alphabet or Google, depending on how you know it. But my most favorite thing to do is I volunteer coach with the Washington Nationals Youth Baseball Academy, teaching them mostly which hand the glove goes on. But eventually, some of my kids have gone on to college and high school ball, which is really rewarding. So, without further ado, here we go. So we're excited to share with you the results of our research to measure the size and shape of the MLB strike zone, as it's called during the game. As we all know, the strike zone is the fundamental measurement in baseball, and a measurement is only as good as its ruler. And umpires are the ruler by which we measure balls and strikes. Umpires are human, which means the measure of balls and strikes involves judgment. And in any repeated event involving judgment, we expect variability in the ruler's assessment. So how good is this ruler? Let's find out. To find out, we collected data on balls and strikes. We used this data to model the average strike zone for the umpire core, as it's called within the game. The surface shows the actual behavior of this ruler. Then we used the modeled surface to explore changes across different slices of the data, whether that's batters, pitchers, seasons, etc. So a quick trip around the base paths with our data sources. So we use the PyBaseball Python library to pull pitch by pitch data from Baseball Savant, which we then combined with umpire information from Smart Fantasy Baseball and RetroSheet to build our complete data set. And our complete data set looks like this. The data frame has about 60 plus columns. For the research that we did today, we used about 9 columns, so including the position of the pitch on the XZ plane, top and bottom of the strike zone for the batter as defined by StatCast, and details of the pitcher, the batter, and the umpire. All in all, we ended up with about 5.3 million pitches called balls and strikes by an umpire for the 15 seasons between 2008 and 2022 across 30 teams and 30 ballparks. We removed any umpires who called fewer than 1,000 pitches, leaving us with 139 umpires, 1,433 pitchers, and 1,688 batters. So what do these 5.3 million pitches look like? So you'll see in this plot, strikes in yellow, balls in blue. The gray box represents the official MLB strike zone. The green area represents the overlap of balls and strikes, AKA our noisy judgments. And this green area is the subject of our investigation. And so for more on that, I'll turn over to James.
Yeah, thanks. So calling back to a talk earlier today, not having been here before, we were definitely aiming for building this talk to experts with the expectation that you're going to replicate our work. So there's going to be some equations that you're welcome to lift and do whatever you want with. The basic analytical path that we were kind of going down was taking the positions of the pitches, do some bucketing, and look at proportions, right? So after we kind of played with this a little bit, and then ended up poking around online, we see that there was some, past work kind of in similar vein, but a lot of it stopped kind of at this point. So if we work from left to right across the slide, you've got the plot we were just looking at. Here's our 5.3 million pitches and kind of where they're landing. This center is the center spot. There's just a little toy graphic kind of showing this gridding process, right? So we've got to bucket them somehow. We ended up going with centimeter square buckets, and then we're essentially polling the data to give us a proportion measurement in each one of those buckets. So that we're going to generate, essentially this grid with some measured percentage proportions in each spot. But we want to go further. So not only do we want to just go measure those directly, but we want to track some information about the error bars on each one of those spots, right? So it's not just a hard number that we're going to run with. And essentially we're talking about survey statistics, right? So we're measuring a proportion in each one of those buckets. And those proportions, come along with kind of well-defined error bars from statistics background. And we can look at grid cell by grid cell kind of heteroscedastic errors, right? And so we want to somehow incorporate all those together to build something that's a little more interesting. One quick aside, we definitely have to deal with some height normalization in the data. So if we're going to be looking at an individual umpire's strike zone, kind of the thing that he actually calls, obviously that varies from batter to batter and stance to stance. So in order to account for that, we're essentially going through the data set and generating some normalizations from the top and bottom of the strike zone. So if we look at the measured top and bottom as reported by StatCast across the pitches that were available, we can essentially do some median, mode, and mean investigations to find a good spot that's essentially the average batter's strike zone top and bottom as reported in the data we were working with, right? And so then at that point, we're essentially just scaling all the other pitches down to that top and bottom. So if a pitch is, 2 inches high for a certain batter, that batter's strike zone gets scaled down by some percentage, and we pull that 2 inches down with it so that it's still proportionally in the same spot, but we've now kind of normalized all of the pitches into nominally the same strike zone that umpire might be attempting to call. The other kind of next step we went through was just to imagine what the general shape of the probability surface we would expect to see would be, right? So we're not imagining that umpires are going to be, perfect machines with infinite precision. If you give them 2 pitches kind of in the same place, most of the time they're probably going to call it the same, but occasionally it's going to vary. And so how is that variance going to move across the plate? Left to right, and then also when you go from kind of bottom of the zone to top of the zone. And so broadly speaking, anybody with data science background is going to see some sigmoids there, logistic curves, whatever you want to call it. We're imagining that things are relatively 0% chance of being called a strike when you're far away from the zone. If you're right in the middle of the zone, we're expecting something close to 100%, something kind of asymptotically approaching it. And then we've got some ramp up and bend over. And so the question becomes, what's the precise shape of that curve? And we're going to use the data to fit it. So here's our sigmoid that everybody likes. Nominally, we've got some noisy data, these black points that are kind of bouncing around. Those are, this is just a schematic, but in principle, those are the values in each one of the grid cells, accompanied with varying error bars, data point by data point. And so we can do some fitting, just a couple of free parameters, pretty straightforward with the individual sigmoid shape. It becomes a little more fun when you try to think how to combine these into a 2-dimensional surface that's giving us, the 3rd dimension of strike probability. So you basically have a single sigmoid that's kind of rising up from one side of the strike zone, a second different sigmoid bending down the other side, essentially just a flipped sign. And then you've got the same behavior coming in from the top. So if you take 4 of these kind of S-shaped curves and combine them, you can see the equation there on the bottom right. These are, this is the full fit, right? So this is literally what we use to fit a probability surface to the data that we're about to show. And there ends up being about 8 free parameters. 4 of those kind of determine the position of the strike zone. If we're drawing something at, say, the 50-50 contour, we can extract those directly from the fit. That's one of the other nice things. Makes it pretty easy in post-processing. And then the beta terms that are listed there are just giving us some steepness. If we wanted to, you could do some enforced symmetry and drop the number of free parameters down a little bit, but we left it as 8. We think it still ends up working fine. So here's the data and the best fit, which is my favorite plot, maybe not the most informative, but if you look on the left, this is kind of the noisiness of the data. You can see essentially that surface is kind of fuzzy. So there are kind of 2 main takeaways from this, I guess. One, umpiring core tends to do a pretty consistent job, right? There's not just kind of wild data points there, right? There's no kind of strangeness going on. Everything's reasonably close to that same shape, but you do see some variability. And then the other takeaway is if you look on the right-hand side, that best fitted surface, which was described on the previous slide, really does a good job of representing the actual shape that we see. Right. So there's some well-chosen, functional shape to the probability surface that we're trying to fit, and it ends up capturing some of the information we expected to see. So we can extract the strike zone from it. But then additionally, if you squint a little bit, you can kind of tell as well that these have some rounded corners on them. They're not the probability surface that we're fitting is kind of matching the behavior of umpires not calling exactly in the corners, perhaps at the rates that they generally should. So quick overview, right? We're gridding the data. We're tracking those errors along the way so we can get some reasonable fits that incorporate how well measured each one of those grid cells may or may not be. And then doing a little bit of work to think about what's the actual underlying functional form that we should take away or that we should fit to. And the reason that we wanted to do this fitting process is essentially it lets us slice the data into smaller and smaller pieces. So as you split by umpire or split by season or look at particular matchups of pitcher versus batter, umpire versus over the course of a season, or maybe particular teams, however you want to thin this down, the data set quickly drops from our 5.3 million pitches to something significantly smaller, right? And so this fitting process essentially lets us smooth over some of that noise and still make some interesting comparisons. And with that, I'll toss it back over.
Thank you. So ta-da, this is our strike zone. So when we look down at our surface on the XZ plane, we get the best fit strike zone surface, which you see here in the dotted white line. The box is a 0.5 probability contour we constructed based on those 4 fit parameters that James described. This rectangle is the umpire's attempt to call the official strike zone. It's just shy of 58 centimeters wide and about 56 centimeters tall. The center is shifted 1.6 centimeters off the plate to the left. This is the strike zone for the entire data set, all umpires, all games, all seasons, all batters, etc. Now is a good time to remind you all that the strike zone we're looking at here and for the rest of this presentation is from the perspective of the umpire. So it's flipped to what you might see on K-zone, for example. So we have our results, but do they make sense? We ran a few tests to ensure the best fit was reliably describing the strike zone. First, we looked at the best fit compared to the overall MLB zone. The best fit surface is the blue dotted box, is just over 7 centimeters wider than the official strike zone, which is the red dashed box. The top and the bottom of the zone are roughly in line for both strike zones. These results seem reasonable, giving validation to our model. One glaring difference between the red and blue boxes is that leftward shift I described. While the official zone is centered over home plate, our best fit surface, as I said, is shifted 1.66 centimeters to the left. We're actually happy to see this discrepancy because it confirms to what we see playing out in the game. This off-center shift in the overall best fit is explained by the difference between left and right-handed batters. Here you see the strike zone for left-handed batters, that's in blue, and for right-handed batters in green. The black lines indicate the width of home plate. So the area of the left-handed strike zone and the right-handed strike zone are nearly identical. And while the right-handed strike zone is centered roughly over the plate, as I said, the left-handed strike zone is shifted nearly 4 centimeters to the left. This confirms what we all know about the lefty strike. And the fact that we can see it so pronounced in the model is another indication that our surface is reliable. We dug a little bit deeper into the lefty strike, and one data story that jumped out at us is that the strike zone for almost every umpire, all 139 of them in our data set, is shifted partially to the left. None of them calls a symmetrical strike zone for left-handed batters. You see this in that top histogram. In the bottom histogram, we're looking at the difference in the aspect ratio between left and right-handed batters. Once again, we see the lefty strike zone is taller and narrower across the majority of the umpire core. We then split the data again between left and right-handed pitchers. What we see here is that the shift is more pronounced when there's a right-handed pitcher. The 2 dashed lines represent right-handed batters are almost identical for left and right-handed pitchers. Both rectangles, however, shift to the left for left-handed batters, as we would expect. But the shift is more pronounced for those right-handed batters. So you see that purple line go all the way over. This chart actually led to a lively discussion between the two of us about the lefty specialists in the bullpen, when clearly our data shows that the right-handed pitchers have a larger strike zone to left-handed batters. It's an investigation for completely another day, but we expect that the benefits of the lefty matchups for pitches where the batters actually swing outweighs any benefit that a righty pitcher might have on called pitches. So you may have heard, though, that the lefty strike has disappeared. So let's investigate. The size and shape of the strike zone has changed since 2008. I don't think this comes as a surprise to anybody in this room. The left plot shows season by season distribution of the best fit strike zone for the entire umpire corps. So the area of the official strike zone is marked by the horizontal red dashed line at the bottom, about near 2,800. There's a small but significant positive slope to successive strike zone areas. So we see the strike zone has grown slightly larger between 2008 and 2022. The plot on the right I find more interesting because it shows that clear downward trend of the best fit strike zones with over height aspect ratio. Overall, we see a 29% drop in the aspect ratio, again, that's with over height, over the 15-year time period. In 2008, the strike zone was wider than it was tall. That ratio decreased steadily, flipping by the time we get to 2018, passing through a relatively square strike zone in the 2016-2017 seasons. Let's look at this from a slightly different angle. This very busy plot shows the best fit strike zone for each season since 2008. Older strike zones are shown in purple all the way to the 2022 zone, which is shown in yellow, and it sort of goes through that color spectrum. Again, the official strike zone is in that red dashed box. Where are we? Overall, the strike zone's width has narrowed nearly 14% since 2008, from about 63 centimeters to 54 centimeters. The majority of the change occurred, not surprisingly, because the left side of the strike zone moved towards the plate about 7 centimeters. The lefty strike largely disappeared starting with the 2017 season. On the Z-axis, the uppermost limit of the strike zone has stayed relatively constant across the umpire, rising by about 2%, not that much. During the period, the bottom of the strike zone, however, is dropped out about 16%. Umpires essentially are increasingly calling the lower strike, which is something that we all see when we watch games lately. So that wraps up investigation into the best fit strike zone surface. Our goal at this stage was really to build the surface and verify its reliability, which I hope we've done for you today. But I couldn't escape without asking it a few questions that actually prompted our research in the first place. There's a lot more to come on this next part, but here's a preview of some of the things we can look at with our new surface. Before we dive in, just a quick reminder that the vertical measurements you see here are not absolute, but they're relative to the average batter as a result of our height normalization process that James walked through. So I'll start off with the first question I get whenever anybody asks me about the strike zone is Angel Hernandez as bad an umpire as his reputation would have us believe? To answer that question, we compared the best fit strike zone of each umpire to the official MLB zone using the intersection over union ratio, or the IOU. So the IOU calculates the overlap of the two strike zones as a percentage of the total area of both zones, as you see the equation on the slide. A histogram of these percentages is on your right. There are two populations of umpires, one centered around 73% and the majority clustering around 85%. Angel Hernandez, much to the surprise of everyone, falls squarely within the primary distribution of umpires. One thing to note about this distribution, however, is that we essentially have two distributions here. The ones on the lower end of the spectrum are all primarily are umpires who are at the beginning of the data set, so the 2008 to 2012-ish period, and the ones who are still umpiring today are further along and cluster on the 85%. So long story short, there's some seasonal effects here that we have to investigate before anyone can convince me that Angel Hernandez calls a game just like everybody else. So I'm going to close with a look at some pitchers and batters. Pitchers and batters are a little bit more difficult to evaluate at this stage that we're at, because while umpires have been aiming for the same strike zone, the MLB hasn't changed the strike zones between 2008 and 2022. Batters and pitchers have to contend with a new strike zone every season. They're essentially playing a different game every year. So we saw this in those season by season plots. But I did want to do some initial investigation, and I swear I didn't just take all bearded white men in blue hats to make this slide, but that's what it turned out to be. I actually chose this collection of pitchers because their careers span a large chunk of the data set, so they're less subject to those seasonal fluctuations that we noticed and have to normalize out at a later stage. Of this group, Kyle Hendricks, he's got the largest strike zone to both left and right-handed batters at about 3,400 square centimeters. Max Scherzer is on the other end at the smallest strike zone of the group, primarily because he's getting fewer calls on the right edge of the plate. The midpoint of Max Scherzer's strike zone is 5 centimeters towards the left edge of the plate. And you'll remember the overall average is about 1.6. So Max is much farther on that spectrum, and particularly to left-handed batters, the center of his strike zone is about 7.5 centimeters shifted towards the left. Long story short, Scherzer is getting the lefty strike call, but not much else. Not surprisingly, the pitchers who we see getting a higher than average proportion of these strike calls are the folks who had the majority of their pitches in the earlier part of our data set. So that's Bronson Arroyo, Josh Beckett, Roy Halladay, Jared Weaver. I'll also put some closers, Mariano Rivera, Jonathan Papelbon, all in this category. But again, their career spanned primarily in the earlier parts of our data set. Speaking of left-handed batters, so living in DC, I spent a lot of time listening, or had sadly spent a lot of time listening to Nationals announcers marvel at Juan Soto's batter's eye. And as evidenced by the fact that I chose this photo, no, I'm not over the trade. Anyway, what the announcers kept saying about Soto is that umpires give him the benefit of the doubt on pitches where he doesn't swing. So I wanted to test that to see whether that's true using our strike zone surface. The evidence so far does not really bear this out. Juan Soto actually has one of the largest strike zones of any newer players in our surface. So on this graphic, you'll see the best fit strike zone. So our measurement of what umpires are actually calling is in the solid line. The dashed line is essentially my best attempt to draw what the official MLB zone would be. So we've got Juan Soto compared to other left-handed batters. His strike zone is quite high. So he's not getting any of those pitches, and even around the edges, still not getting the benefit of the doubt. That's in contrast to a player like Joey Votto, who is actually really well positioned for us to analyze because his career spans most of our data set. And what you can see about his strike zone is that it's compressed all around the edges, leading me to want to further investigate whether Joey Votto actually gets the benefit of the doubt from umpires on balls where he doesn't swing just because of his reputation as having a great eye. I grew up in Boston, so I'm still a Red Sox fan, and selfishly, I'm really tired of all the complaints about Aaron Judge gets unfairly called for low strikes. So I set out to investigate this. Unfortunately, for my humility, it's true. Turns out Aaron Judge's strike zone, as it's called, is about 6 centimeters lower than the strike zone for the rest of right-handed batters. Dang it. However, what I do not hear yes announcers complaining about is any calls near the top of the zone. And it turns out that according to our measurements, Aaron Judge's strike zone is actually about 10 centimeters shorter than it should be, which means his overall strike zone is smaller than the average MLB batter, which is kind of crazy to think about given his frame. Again, we did the height normalization, but there's probably something about his just giant 6'7" frame that's causing this. The last one we looked at, I just wanted to take a quick look at someone with an upright stance. So I chose Bellinger, and what we found is he actually has one of the smallest strike zones, as actually called, during our game, even when we look just at most recent players. Nearly all lefties were not seeing the outside strike on these newer players, but where he stands out is really his ability to get the call on the inside of the plate and the upper part of the zone. I just talked for a long time, so I'm going to turn it back to James to close us out.
Thanks. So calling back to kind of Rebecca's talk earlier about making sure to mention limitations, I think this last slide, and we'll go back a couple as well, are good points to talk about the height normalization again. So when we talk about Judge's strike zone being X centimeters smaller than somebody else's, or X smaller than the average, remember, we have to scale those kind of back out into some absolute units. But what it's really meaning is it's smaller than you would expect it to be for his height compared to the average batter, right? So essentially umpires are giving him a larger strike zone because of his height, but just not as much larger as you might otherwise expect. Similarly, there's a lot of work that we wanted to do and essentially ran out of time. The majority of the stuff we looked at was essentially slicing the data set along one axis. So we've got the pitch data, let's bucket by umpires and then fit a best fit surface for each individual umpire and look at some variability across that. But in principle, you can continue to slice the data along further directions. The fitting process helps smooth out some of the number statistics issues. A full sensitivity study is still kind of ongoing. My Linux box at home is crunching on it right now. The idea would be to really kind of nail down just what sort of sample size you need to worry about. Conveniently, a lot of pitches are near the edges of the zone, which is exactly where we want to measure it. So I think we can end up getting down to some pretty small sample sizes to still get a decent estimate and stick some error bars on some of those fits as well. And then, just kind of jumping back to this guy, once we looked at these season by season changes and how clear they were, we immediately knew most other conclusions we were going to come to were going to be with a big asterisk next to them until we had a chance to start slicing the data into lots of directions. But in particular, here, this is a good example. First time we looked at this plot, I thought it was really interesting. Two populations of umpires, kind of curious what's going on, but it's largely time effects where the umpires who were near the end of their career and early in the data set were calling that differently shaped zone. Whereas the umpires who have spanned the full data set, they're kind of averaging that out, right? So we can go through and build season by season by umpire strike zones and start doing some more tests there. But as Emily Ann said, this one is a pretty busy plot, but I like it. It kind of summarizes what you're looking at here with the season by season data, but as the strike zone appears. So you can see, earlier we've got that wider, shorter strike zone, and we're slowly kind of morphing into what we see today. So I think good spot to stop there and ask for any questions.
Well, first one, a little more objective. Did you take into consideration the average height of the player? I don't know if that's changed at all over the last 15 years.
So the normalization happened at the full data set level. So we essentially took, the reported top and bottom of the strike zone from StatCast for the entire data set and used that to normalize. So we've effectively normalized to the average batter across the whole data set. As we would go back and potentially slice this multiple ways, then we would potentially normalize by the average in that year or the average in whatever bucket, we happen to be slicing it in.
So it's become narrower but smaller.
Mhm.
When they're smaller, maybe the average hitters.
So broadly, that comes out in the normalization. It is kind of smashed in there because we did it across all seasons, but in principle, it's larger compared to the average batter. And so if we went back and did a season by season, then we would be looking at those potential changes in batter height across seasons. Yeah.
My other question is a little more subjective. You showed the 4 pictures up there, and if I read that right, it looks like Juan Soto is getting posed more so than Joey Votto.
Yep.
Joey Votto is 39, Juan Soto is 23. Is there a respect factor, do you think, in the umpires that might be taken into consideration?
That's initially what we set out to measure. It's like, are there just umpire biases that we can see with this method? And I think that's exactly what we're seeing, despite the constant, I can't even tell you, for those who listen to Nationals broadcast every night, it was just marveling, oh, umpires must give Juan Soto the benefit of the doubt because he's got such a batter's eye. It was like his second year in the league. So how much respect was he actually earning? So it appeared so to the naked eye, but statistically, it doesn't bear it out. Whereas Joey Votto might well be. And so that's why I do like the comparison between the two. Both batters known for their eye, but only one is actually benefiting from it. Yeah.
Go for it.
Early on, you showed a plot of the real data of where strikes were being called in the zone, and it was pretty round versus the expected strike zone obviously is a rectangle. So I'm curious about your decision to model the strike zone as a rectangle versus a more round function.
Sure. So it was a couple of reasons. I mean, the actual fitted surface does have kind of rounded corners. The way, if you look at that kind of pillar that's there, it does kind of account for, we know that, umpires aren't really calling right in the corner necessarily. But at the same time, we wanted to kind of assume that umpires are attempting to call a rectangle, right? Like they're trying to call that. And so you can see it here as well, right? So this is our best fit strike zone, but if you look in the corners, like the actual probability surface is lower there. So there's just a little bit of a display issue of what do we want to call the strike zone after we fit this probability surface. And so we essentially took the 50-50 contour at the center of the left, right, top, bottom and extended those out to generate that rectangle. So it's essentially if umpires were calling a perfect rectangular strike zone, what's the size that it would actually be? And then that made it easier for us to compare to kind of MLB regs, right? Like they're actually wider than you'd expect, and we can make comparisons of the area a little easier. Yep.
I think that's most times we're left-handed hitters versus right-handed hitters. And I'm wondering if there's anything to do to the umpire slot in between the catcher and the hitter. I'm wondering if there's a sort of a left eye, right eye dominance thing that allows you to process that corner that hits the break or hits the break pitcher, not the hitter. I wonder if there's something that you positioning of umpire, or maybe because the catchers are all left-handed to that side.
Yeah.
And does that help? I don't know. Is there any hypothesis on what it is that something that is sensitive?
So I don't know that there's really anything in the data set we had that would let us do it. We did speculate about like, hey, could we get some video and do some object detection and where are the umpire's eyes and those sorts of fun things. The only thing we really pushed for, partly from time constraints, was just a quick scatter plot of umpire height, right? So we pulled in biographical data, and so we did, kind of umpire height versus the area and aspect ratio, et cetera, of their best fitted strike zone, and didn't really see much of a correlation. So like kind of the only thing we kind of pushed in that direction with was nothing, but it didn't surprise me. I wasn't holding my breath for that one. But yeah, I definitely think that there's some other avenues. One more question, I guess.
I'd be curious if being a small and strike like catchers in your data set matches up with the pitch framing methods or anything, and whether that's whether the pitch frame, I assume the pitch frame is based on the idealized strike zone, and if your model strike zone matches up with the pitch frame versus who doesn't.
So yeah, that's kind of right down the middle of what we were kind of imagining this would be useful for. The first half of the talk kind of came out of something else, and then we were just chatting about it and kind of realized it was an interesting ruler to go measure other things with. And so potentially, automated strike zone stuff, what do you actually want it to call? If you wanted to model umpires from the last 5 years, here's what it actually looks like. Pulling in pitch framing and kind of saying, catchers are getting it further from that umpire's strike zone versus some idealized surface. Like there's opportunity to roll it into whatever kind of other thing you're trying to measure.
Yeah, just very practically, that was one of the first questions that I wanted to answer, and then realized catchers are not in the data set, and the process of matching them, given our time constraints, just wasn't there. So if any database folks are out there listening, catcher data, please. All right. I think that's everything. Thanks so much for listening. Appreciate it.
Thanks.